Hello, everyone, and welcome to the second presentation in the Water Resources Institute Water Connect seminar series. During this seminar series, we're looking to focus on flood-related research by UVM faculty and flood experiences in communities. My name is Harrison Myers. Hello. I'm a PhD student in civil and environmental engineering and a Gunn Fellow here at the University of Vermont. I'm very excited to introduce today's talk by Eric Roy with the Rubenstein School of Environment and Natural Resources, entitled Restoring Wetlands to Mitigate Flooding and Improve Water Quality in the Lake Champlain Basin. Eric is an assistant professor of environmental sciences focusing on ecological design. He leads the nutrient cycling ecological design lab at UVM, working at the interface of ecology and engineering and focusing on water, food systems, and resource management. Nutrient cycling is the common thread that ties Dr. Roy's different research interests. His group quantifies the forms, biogeochemical transformations, and fluxes of essential nutrients for life on Earth, aiming to 1, clarify important processes that underpin ecosystem function, 2, identify opportunities for beneficial intervention, and 3, design systems that achieve nutrient management objectives. This talk will be about 30 minutes with 15 minutes of Q&A at the end. We ask you to please hold your questions until the end. And welcome to our remote guests. If you are joining via Zoom, you can enter your questions into the chat box at any time during the presentation. I'll now turn the floor over to Eric.
I'm just not seeing how to change my slides. Oh, there we go. Okay.
It's a little okay in the upper right too.
Yeah.
And you can hide the others. That's the floating meeting controls. Yeah.
Perfect. That's much better. Okay, let's get going. 30 minutes might be a little closer to 35. I'll do my best. So I'm going to talk today about restoring wetlands to mitigate flooding and improve water quality in the Lake Champlain Basin. I'm going to kind of just overview the flooding piece and talk mostly about improving water quality, but they're definitely very tightly connected. We are lucky here in Vermont, where we have one of the best examples I have ever seen of wetlands reducing flood peaks. We have the Otter Creek, which runs from south to north, south of us in Vermont. There's 2 gauges on that system that we look at a lot, one in Rutland and one in Middlebury. So Rutland is the upstream gauge and Middlebury is the downstream gauge. And this image has become very kind of iconic for Tropical Storm Irene in 2011. You can see here that the line here is in Rutland. And you can see this high, fast, intense flood peak that went between 15,000 and 20,000 CFS. And so that's the upstream site. At the downstream in Middlebury, you see a much lower peak flow. You kind of see this almost biphasic dynamic where it kind of starts to increase, similar to Rutland, but then slows down for a while, speeds up a little bit, but never reaches anywhere near the same peak flow. And this is just a really great example of why it's important to have connected floodplains and wetlands and river corridors. So all this green here between these 2 gauges is accessible floodplains. This is one of the largest kind of floodplain wetland complex in the Northeast United States. And so when that water moves through Rutland, it then enters a network of river corridor where you can spread out into the floodplain, access different wetland environments, really decreasing that peak flow, saving Middlebury from potential flood damage, and also providing other ecosystem services. And so that was in 2011. That was the Tropical Storm Irene plot. And I don't have a similar plot here, so we're cut off at the bottom a little bit. But this is from Kristen Underwood and a student she's been working with. Similar dynamics for some of the recent big flood peaks we've seen in July 2023. The peak flow at Middlebury was less than 50% of the peak flow at Rutland, despite being the downstream gauge. So this is a great example of what we would love to recreate along rivers throughout the United States, is can we decrease flood risk by creating more well-connected floodplain and wetland networks that can accommodate water as it moves downstream and protect those downstream people and infrastructure. And so as part of this, we also think a lot about water quality. In the Lake Champlain Basin, the big emphasis is on phosphorus. Phosphorus is the limiting nutrient that largely affects how big and problematic algal blooms can be in Lake Champlain. And this is similar for other freshwater ecosystems across the country and world, including systems like Lake Erie, in Ohio, Lake Okeechobee, in Florida. Phosphorus management is a big deal in a lot of places. And so we're really focused on it here because of the EPA TMDL that requires us to reduce phosphorus loading into Lake Champlain. And this is a really, really difficult problem to solve. There are no silver bullets when it comes to phosphorus management. And it's a persistent problem people have been working on for decades. And to be honest, struggling to make a lot of measurable progress. Cases. Sometimes the new data comes in and the algal blooms aren't any smaller and the phosphorus loads aren't much different, despite a lot of good intentions and effort on the ground. So one idea out there is that when we have these kind of persistent environmental problems, we should look to identify nature-based solutions. So these can be more cost-effective in many cases at reducing nutrient transport downstream and also provide other benefits besides just phosphorus load reductions. And wetlands are a classic example of this, long known to provide large-scale water filtering services. So if we look at the wetland phosphorus cycle, this is a complex diagram, but it's actually a simplified diagram of what's going on out there. But we have different forms of phosphorus in a wetland. The two key distinguishing things are we have forms in particulate form. So these are phosphorus forms that are attached to particles. And that's one important thing about the phosphorus cycle and what connects it to kind of the movement of sediment and erosion issues is that phosphorus often tends to be associated with particles. But we also have dissolved phosphorus out in the environment. And while we have become pretty good at trapping particles, trapping dissolved phosphorus has been much more challenging for us. And so phosphorus can move between dissolved and particulate forms, and then those each have both inorganic components as well as organic components. And this particular one, DIP, which is also commonly referred to as soluble reactive phosphorus or SRP, I'll be talking about a lot. And that's one that has been especially slippery in phosphorus management, where we think we're doing a good job and then we realize the dissolved P issue is kind of not really improving or maybe even getting worse. Now, what we want to do with a wetland is there's kind of two ways we can store phosphorus in a wetland system for longer periods of time. One is that wetlands are good at accreting organic material. So as they accrete that organic material, some of that will become pretty stable and it will hold phosphorus as part of those kind of organic particulates in the soil. And those can accrete and build up over time. And some of them can remain relatively stable. The other way we can store it for longer terms is to form particulate inorganic phosphorus through binding with metals like iron, aluminum, or calcium. Those can also, in some cases, remain quite stable over time. So that's what we would like to see, but oftentimes, we have phosphorus moving into these other components that aren't quite as stable. A little wonky, sorry. So some more background. We know wetlands can retain phosphorus. That's been studied for decades, but making generalizations about how much they can retain is much harder to pin down. And so there's been several review papers that have looked at this for different types of wetlands. Often we see wetlands like in the 30 to 60% phosphorus load reduction range, but it can vary a lot. And in most cases, the retention of phosphorus is driven by trapping particles. So we're having those particulate phosphorus forms captured in the system. And in some cases, there is potential for net P export. And when this happens or has been observed, it's typically been driven by the dissolved P loss that can occur. And two types of systems that are relevant to our work in my lab and the broader UVM team are floodplain wetlands on formerly farmed land, and I'll explain why that's so important in Vermont in just a second. And then we're starting to move into conserved or restored non-floodplain wetlands, which also provide some flood mitigation services by just providing more space on the landscape where water can be retained and slow it down before it reaches streams and rivers. Okay, so if we look at, there's been some studies done in the past at where could we restore wetlands in the Lake Champlain Basin. And so we took some of the outputs from that previous work and just overlaid it with some land use layers. And 94% approximately of wetland restoration candidate sites in the Lake Champlain Basin have been farmed as recently as 2016. So when we talk about restoring wetlands in Vermont, especially in the Lake Champlain Basin, we're primarily talking about one type of conversion. We're talking about conversion of agricultural land back to wetland. Of course, historically, this was probably wetland to begin with, but these were kind of lands that made sense at the time to convert to farmland because they had favorable properties to grow crops. But these days, some of these sites are either difficult to farm due to increasing kind of wetness in these fields, or there might be other economic dynamics on the farm that make it favorable for a farmer to put some of the land into an easement versus continuing to try to farm this piece of property over time. So that's what we're talking about here usually, is converting farmland back to wetland. And this is one reason entities like the USDA and NRCS are very involved in this process here in Vermont, because they're in the business of conservation easements on former agricultural or current agricultural land. And so we have this question of mass balance. We have, on one hand, we know wetlands are good at trapping particles when they're inundated with floodwaters or any other type of influent. And that works in our favor for P retention on the left side of this image. But we also know that there's some factors in place that could cause phosphorus release, and particularly the diffusion of soluble reactive phosphorus out of soils during inundation events. And the literature to date has suggested that this is especially true for former ag land because soils have been fertilized over time, so they might be higher in phosphorus and contribute to this mechanism on the right. And so I'm going to try to fairly quickly go over what has become a kind of a growing body of work here with several collaborators that started around 2018. And I'm going to kind of walk you through some different phases, and including where we're headed in the future. So it all got started with the Lake Champlain Basin program project that was funded for a start date in 2018. And then we were able to acquire some additional support from the Gund Institute, Vermont DEC along the way. And we started by looking at soils across several riparian sites, 42 total in Vermont, to better understand soil properties that are related to these dynamics, and then to do some really intensive field studies for 3 riparian wetlands. In that process, we developed a wetland phosphorus model that I'll talk about, and we use that model to simulate several plausible scenarios at those intensive field sites. And then from that, we attracted some funding from USDA and NRCS to expand our work to an additional 5 riparian sites, all of these being NRCS conservation easements, and then to also estimate net phosphorus retention at those sites. And then finally, we're kind of looking ahead, we're going to be moving into non-floodplain systems. So I'll just say a little bit about that, but we have funding now to do additional field work as well as additional model work to better understand how these systems function for phosphorus retention. And all of this is leading to what we're calling a wetland phosphorus retention calculator. So this is a complex topic, and we've been trying over time to boil it down into simpler and simpler tools that can help decision makers on the ground understand the water quality services offered by these systems. And there's also been some additional LCBP funding and Cairo funding that has supported kind of tangential work to this project that have fed into all of this stuff I'm going to show you today. And so, as I mentioned, we started by looking at soil. So, because the dissolved P dynamics are so dependent on the nature of the soils, it's really important to understand, what soil properties affect dissolved P dynamics and how. And so we really started there several years ago. You can see this map on the right. We were working throughout the Lake Champlain Basin, collecting soil samples from rapid assessment transects. We did some more in-depth intact soil core experiments. Then we leveraged some past data that had been generated by UVM researchers before we got started on all of this. And one of the pieces of this that has been really useful is these intact soil core incubations. So these, we go out into the field. We've had numerous undergrads over the years that have helped us with these experiments. Harrison helped us with these years ago, way before he was a PhD student. And what we do is we collect intact soil cores.
So the other thing that we have out on Bright Space is what?
To simulate flooding on top
What
of
was an assignment that
understand
Anna put up?
how that dissolved P dynamic between the soil and the water will work for different soils. And so we started by doing this 20 plots across 14 sites for a paper we published in 2022.
So you guys need to communicate that with your
each thing on the x-axis,
whomever, because we need to coordinate those times.
and the gray dots are
That is
the
really
anaerobic
critical.
incubation, so when we purge cores with nitrogen gas daily, and the red dots are aerobic incubation, so we purge the cores with room air daily. And you can see there's a range in this final SRP. So after about 2 weeks, things tend to level out and how much SRP is released into solution in the overlying water. And depending on site, the difference between the aerobic and the anaerobic can be small or large, but typically we see higher release rates when there's anaerobic or low oxygen conditions. And so this was our first step in just understanding what's the potential for these different soils to release dissolved P, which was an important first step. We then tried to understand what soil properties predict soil soluble reactive phosphorus release from soils. And so we looked at several things. I'm just going to highlight 3. So there's these 2 soil metrics that I've come to really like. One's called PSR. It's the phosphorus saturation ratio. So that's a function of particular forms of phosphorus, iron, and aluminum that are in soils. And then a related metric on the right is called soil phosphorus storage capacity. And that's probably my favorite because it's very intuitive. If you're negative on this metric, it's bad. And if you're positive on this metric, it's good. So it helps make sense to me. And what you can see, if this is final SRP on the y-axis for a soil phosphorus storage capacity, when it is negative or near 0, that's when we tend to see the highest release rates in the lab of SRP into the water. We have a positive soil phosphorus storage capacity. We tend to see very low rates of SRP release. And the other one that's cut off on the bottom is year since farming. We also have found that the longer a site's been in restoration or conservation, the lower the amount of phosphorus released from the soil into water. So this is a good thing. This means that over time, we expect dissolved P release from these soils to become less problematic. And then we looked at the broader number of sites and samples that we collected. And these 2 soil metrics I like, the P saturation ratio and the soil P storage capacity. And this just kind of makes the same point with more data that for the more frequently farmed soils that have a negative soil phosphorus storage capacity, a much greater propensity to let go of dissolved P when in contact with water. Then we just published a paper today, actually, good timing. This paper looked at different ways to predict agricultural soil P metrics in the Missisquoi Bay watershed. And one thing we found when we were doing this study is that a lot of the hot, where we predict relatively high soil test phosphorus was along river corridors. So this means that for these sites that are currently still being farmed, we might run into these types of scenarios occasionally out there. So we need to kind of provide guidance on how to deal with that situation if that's the case. And this is just one example. This is kind of a river network coming in here. You can see these orange polygons. Those are sites with higher soil test P by our predictions. All right, so to jump into this initial field study, 2 of these sites were along the Otter Creek, which I mentioned already. And then one of these sites was along Prindle Brook, which is a tributary to Lewis Creek. And this was a very deep dive. We measured way too much and really wore ourselves out trying to figure out what was going on at these sites in terms of phosphorus dynamics. We were measuring water samples, soil samples, monitoring hydrology through these sites. It was a really intensive effort. So a few key findings from that effort from those 3 sites. So the first is, this stuff we're seeing in the lab, is it actually happening in the field? Is there evidence that this dissolved P dynamic issue is real? Otherwise, we can just focus on particulates. And so if you look at this middle panel here, this is the river at Otter Creek in these triangles, and this is total suspended solids on the x-axis, total phosphorus on the y-axis. So if all that's going on out there is trapping of particles and removal of phosphorus, we would expect data to kind of remain largely along this red line, because that's what we see in the river. But instead, when we move to the wetland, which is the black dots, we see, it really deviates from that line. And we see plenty of cases where we have low suspended solids in the water, but relatively high phosphorus. And these are situations where dissolved P release from soils is likely playing an important role. So that occurred at 2 sites. Then when we look closer at that data, when that does occur, we take low dissolved oxygen conditions. So this is periods when the water's sitting on the wetland for a while, the oxygen gets depleted, and then we start to see this release of dissolved P. So this provided some field evidence that yes, this is important. We do need to try to understand this dissolved P piece in order to really come up with good estimates for overall net retention. But that's just one part of the story, and to be honest, that's the scary part of the story. The rest is good news after that. What we had to do in order to make sense of all of this is that was just thinking about the potential for dissolved P release, but we also have to measure and model the deposition of particles in this system to understand how much particulate phosphorus is being captured. And then we can have that on one hand, and then the dissolved dynamics on the other, put those together and come up with net phosphorus retention. So we can't directly measure this in riparian systems. It's not possible. There are no confined inlets and outlets. So we have to model, and we have to do our best to calibrate and verify that model to make sure it's doing at least a decent job of representing reality. So we built a wetland phosphorus model in R. So we leveraged some past wetland models, but this model is unique in how we treat soils. We rely a lot on that soil phosphorus storage capacity concept for the dissolved P dynamics. And then we also model, cycling of plants, trapping of particles, and then conversions of phosphorus, transformations that can occur within the wetland. So we had 2 years of field data from 3 sites that we used to kind of calibrate and verify the model. And it, at the end, spits out mass balance estimates for both dissolved P and particulate phosphorus and the combination of the 2. And so if we look at that dissolved P results, so these are the 3 sites here. And then on the x-axis, we have a stream concentration factor. So 1x is the actual concentrations of phosphorus we saw coming into these systems. 0.5x is half of that, and 2x is twice that. So results are really dependent on the concentration of phosphorus in the water entering the wetlands. And at 1x, you can see at one site, our median was around 0 for dissolved inorganic phosphorus. So not a whole lot of net retention or release. But at our other two sites, we did see net release of dissolved inorganic phosphorus. And this, again, really varies by the concentrations in the river. The situation is better if you're in a river with higher concentrations of phosphorus to begin with. But then if we look at total phosphorus, this is a much rosier story to tell. So, while there is some net release of dissolved phosphorus, when you take into account all the capture of particulate phosphorus, you tend to end up in the black here and have overall net positive phosphorus retention efficiency. So it varies by site, it varies by some of our assumptions about particle trapping that we use in the model. But overall, when we looked at a whole bunch of different scenarios, I think we did 108 scenarios in general in this paper that was just published this past year. We found net total phosphorus retention around 35% on average, but it varied with a standard deviation of 30%. And on a mass basis, that's anywhere from just a bit net negative to almost a 0.5 gram of phosphorus per meter squared per year. And so through this work, we've started to better understand what controls phosphorus capture in these systems. And it's really, we kind of boiled it down to 3 key kind of factors and then some particular measurements for each factor. So the nature of flooding matters in a system in terms of how often is the system flooded, what is the hydraulic residence time of water moving through that wetland, and what is the overall hydraulic load to the wetland, the amount of flow passing each unit area. But surface water quality is even more important. So when we have rivers with high phosphorus concentration to begin with, that's where we see the highest net retention, which makes sense. And we've picked a few metrics that we can represent in the model that capture that. And then wetland soils are the other factor that really matter. And part of it is how, this kind of balance between organic and mineral components of the wetland soil. And then importantly, that soil phosphorus storage capacity. So for example, if we look at sites 1 and 2 on this kind of conceptual framework we published last year, if you're in a site that has relatively low stream dissolved inorganic phosphorus, relatively low stream total suspended solids, and a high hydraulic load, like number 1 here, you're probably in a situation where net loss might occur. If you're on this side of the conceptual diagram where you have high concentrations of phosphorus and TSS in the water, high soil phosphorus storage capacity, and a high hydraulic load, this would be an area where we would really expect net gain of phosphorus. And most of the sites we've looked at and modeled are kind of fall towards the blue on this figure, but there are some situations where we might start to creep into the green part of this figure. And so that was the kind of first round of work. And then we've picked that up with additional work at 5 riparian wetlands as part of our NRCS SEEP project. SEEP stands for the Conservation Effects Assessment Project that's run by NRCS. So they're really interested in being able to quantify the water quality benefits provided by these systems post-restoration. And so this has included a lot of the same fieldwork, but a more kind of targeted, focused effort. We learned a lot of lessons in the first study that we've applied to become more efficient, but we monitor hydrology out at these sites, dissolved oxygen at the soil-water interface. We really focus on getting water quality measurements during the rising and falling limbs of inundation events. That's kind of the fun storm chasing part of the project. And then we're looking at accretion of mineral and organic matter on the surface of the wetlands. and a few specific soil properties, including that important soil P storage capacity. We've used HEC-RAS models to inform our estimates of hydraulic retention time. And then we're using that wetland P model to come up with the overall net P retention estimates. And so this has been focused on a few sites in Otter Creek, one of which overlaps with the past study, and then 3 sites along the Lemon Fair River, all former ag lands currently under conservation easement. The Otter Creek's a larger river, also has a different dynamic where it drains snowmelt, and the Lemon Fair is a smaller river, kind of more affected by very local precipitation dynamics. Time since farming varies from 3 to 14 years at these sites. Sorry, this is a little cut off at the bottom, but this is across 2022 to 2024. This is just the dates along the bottom that's cut off here. And this is water level in one of the Otter Creek sites. When we first started doing this work, we were very naive and we're still learning a lot. And we thought, oh, we're going to be monitoring like a big snowmelt flood pulse in the spring. And maybe it tends to be higher flows in the fall. Maybe we'll have these kind of seasonal pulses that we'll monitor. That's not what it's been like at all. We monitor floods all throughout the year, little floods, big floods. We have all these freeze thaw events where we have snow thawing in the middle of winter and generating a small flood pulse out there. And we do our best to get out there and monitor as much as we can. So these little red dots are when we're out there. What we want to capture when we're out there is the nature of the river water during the filling period and the nature of the wetland water as it's draining. And so it's tough data to get, but we've been lucky to generate a lot of it so far. So that's what the flood dynamics, this is the big 2023 flood. That biggest peak is the July 2023 flood. So you can see we had almost 3 meters of water on top of the wetland. So huge, huge event. We've had some other big ones too. And then this is in the Lemon Fair. Everyone refers to it as weird. It has kind of interesting dynamics where it kind of outflows to the Otter Creek. So when the Otter Creek is high, it gets kind of plugged up and water kind of fills in that river. And it can stay wet there for quite a while. But we've seen lots of events in the Lemon Fair as well, different timing than the Otter Creek. But we've been able to capture a lot of them in terms of our sensors as well as some water sampling. And so we're still at the stage in that project where we're kind of gathering all the field data and kind of running through our first assessment to see if the indicators are good or bad in terms of net P retention. And so these are the 4 things we look for. We ideally want to see concentrations of soluble reactive P, total P, TSS, and influent river water greater than the wetland draining water. And then we would love to see water well oxygenated because that dissolved P release tends to happen most prominently when waters are anaerobic. We're also looking for accretion that's indicative of sediment deposition during flood events. And we'd love to see soils that have a positive soil P storage capacity, meaning they have less potential for internal SOP release. So there's a lot of data here, but I summarize it right at the top. Are we seeing higher concentrations of phosphorus and sediment in the influent river water than the wetland draining water? Yes, in most cases. For most sites we've looked at and most individual events where we have good data, we tend to see concentrations of these constituents either similar or lower in the wetland draining water compared to the river water that fill these systems. So if concentrations are either staying the same or going down, that pretty much guarantees that we're going to have net retention in the wetland because even if concentrations stay the same, not all the water that enters the wetland comes back out. Some of it stays there for a long time and evapotranspires over time. So that looks good. Is the water in these systems well oxygenated during floods? Yes, in most cases, but we do see some anaerobic periods, especially at particular locations within certain sites. So these are dissolved oxygen sensor data that we've collected. This is throughout 2022. at our 5 sites. And you can see for some of them, they kind of stay aerobic almost all of the time. But we do see, you know, occasional plots where we have more anaerobic conditions. Similar story for 2023 and 2024. But the good news is that the field SRP concentrations during these falling limbs, when the wetlands are draining, tend to be much lower than we would predict based on lab incubations under anaerobic conditions. So we don't really think we're having that kind of worst case scenario play out in the field of anaerobic conditions with high SRP release. In terms of, are we seeing a lot of capture of sediment? Our best measure of that is accreted inorganic phosphorus, which is shown here in these bottom plots. Again, a little cutoff. These are 2 different years. The blue period is the 2022 to 2023 period. And that was with the July 2023 flood. We saw relatively high amounts of inorganic phosphorus kind of deposited on the wetland surface. So that's also looking very promising in terms of capture of phosphorus within these systems. And then finally, our soil phosphorus storage capacity metrics are all positive at these sites, ranging from about 260 to almost 2,600 milligrams of phosphorus per kilogram. So we're kind of in the right side in the positive territory on that graph on the right, which also is a good indicator that we're likely not going to release a lot of dissolved P. So far, all of the multiple lines of evidence from the fieldwork are good. The next step is to use our wetland P model, kind of do some similar simulations to our past study. I think we'll probably see higher mass retention rates for these systems because one, we've seen bigger events, and also the lemon fair tends to have higher phosphorus concentrations to begin with. So for those sites, we'll probably see rates of P capture that were higher than ones we've estimated in the past. And this is all going to be used to develop streamlined guidance for riparian wetland restoration, including quantitative criteria for NRCS. So just a couple words, and then I'll wrap up. Hopefully we have time for a few questions. But where we're headed next with the non-floodplain wetlands piece, we're kind of streamlining our approach. We know more what we need to focus on to get good wetland phosphorus model simulations. So we're measuring some key things in terms of water level and hydraulic residence time, improved water quality, few soil metrics, and some vegetation feedstocks at a variety of sites. And I'll just kind of end here. Where we want to get with this is a place where we're using both the floodplain data and the non-floodplain data to kind of generate simulations in the wetland phosphorus model that kind of give us a better understanding of how different site conditions affect how much phosphorus is retained in these systems. And this is all leading towards, it's been a complex long-term process. At the end of it, it will be almost a decade of work to get to a point where we have a relatively simple tool that people can use, a spreadsheet calculator that kind of is informed by probably hundreds of simulation runs by our wetland phosphorus model of different site configuration parameters. And at that point, you'd be able to put in an area, put in a soil parameter, something about kind of where along the spectrum of water quality your river is, and a few vegetation or hydrology parameters, as simple as possible, and come up with that kind of golden number that everybody wants, which is kilograms of phosphorus per year on average retained. So, I mean, this has been a long road, but our hope is that will lead to something that's easy to use, but also has a lot of scientific rigor behind it to help us feel confident that we're not just pulling these out of the sky, that this will help us select sites that are going to perform better and differentiate those from those sites that are not likely going to perform as well for meeting water quality goals. So a huge number of people have worked on this, including, I haven't come up with a firm number, but I think we're probably over 30 undergraduates at UVM have engaged in research with us on this topic, including many honor species. Tiffany Chen's a huge part of the lab, Adrian Weidman, many others, including Harrison, many faculty. We've had a variety of funding. It's been a really fun ride. Happy to answer any questions.
I know that I've heard a lot of things that currently there's a lot of projects in like this particular like watershed to restore riparian buffers. Are you making any attempt to make your research available to these like community projects that are trying to improve water quality?
Yeah, my hope is that, the way those projects tend to work is when they're in the scoping phase, they'll collect site information. And in the stormwater world, they would take that information and kind of put it into one of the available tools to help them estimate, all right, this project is likely to kind of remove this much phosphorus from water. And that helps make evaluations on which sites to prioritize, which projects to prioritize. So my goal is to create something that works in a similar way so that people thinking about those projects, like a wetland restoration, could collect a relatively small number of input parameters and then come up with some estimates of their own, and that can be used to help justify those projects.
Looking behind me. Can you say a little bit more about where the non-floodplain wetland sites are? Are they up in the uplands? Or are they just out in the matrix on farm fields, but not in the river
A
corridor?
little bit of both.
And then,
yeah.
like, what difference does the phosphorus retention or release make unless they are somehow connected to the river network? So I'm curious about where, and if you could be a little bit more specific.
Yeah,
And
so,
like, what's the connection into streams or rivers?
so I'll have to do a little arm waving here because we're meeting with our project advisory committee early next year to finalize site selection for that project. But my goal is to have sites that are along a continuum of temporary connection with downstream surface water. So some of these sites, the water will get, like, if it's surrounded by mountains, right, and water just ends up in there, we're not that worried about it, right? That's not a case we're super interested in, although we might want to just have a way for people to estimate what service is that currently providing right now from a conservation standpoint. But there's other sites where they are typically disconnected from surface waters downstream, but then during high flows, they have temporary connections. So water can move through those systems and then kind of move down through the stream network eventually. And so for those sites, there is the potential that they are trapping phosphorus that if they were destroyed, they would not trap, and that could make it downstream. So based on our conversations so far, some of these are in agricultural areas where they're kind of surrounded by agriculture, and there's kind of one depressional wetland that's receiving water during higher flows. And in other cases, it might be in some of our kind of more mountainous topography where we have these systems. And the wetlands program and others are just interested in better understanding what's the phosphorus kind of retention value that those sites are serving, both from a conservation standpoint, why do we want to protect them? And then if there's an opportunity to restore sites like that, what potential value they could provide from a water quality perspective. As well as I should always say, I always try to say, phosphorus is one thing we think about with these, but they provide habitat, they provide recreation, they provide carbon storage. So just keep that in mind as well.
So given that like soil metrics and time since farming is such an important driver of phosphorus dynamics and like risk of internal release, and 94% of potential restoration sites have been formally farmed, would you recommend, like, if a field just stopped being farmed, would you recommend a buffer period for that field where it's kind of not being farmed but not reconnected yet? Or would you say just reconnect it and kind of let what's in there leach out, and eventually it'll reach equilibrium?
It depends on what your time horizon is, right? Like if you're really worried about impacting phosphorus loads this year, like you might take one approach. If you're thinking in terms of decades, I mean, everything we've seen so far suggests that the decay rate of SRP release is, within the first decade, you've come way down. So if we take the long view, which I think we should when it comes to restoration, then I'm not that worried about it over a long period of time. But that doesn't mean there aren't things we could do in the short term just to try to reduce it. So there might be ways to, continue harvesting without additional nutrient inputs for a year or two before reconnecting the hydrology, right? Just try to draw down phosphorus a bit more in the soil before you make that reconnection. That's key. Is I think the worst case scenario we're looking at is a cornfield in a riparian area that's been heavily fertilized, stopping and then immediately reconnecting the hydrology. I think that's going to lead to the bad outcomes. So just having some guidance for NRCS and other practitioners out there about if you do encounter that situation, what are some things we could do to maybe mitigate it a little bit and hopefully release as little of the phosphorus as we can. But at the same time, if you take the 50 years view, some of it is going to leach out, but over time, these systems are going to get better in that regard and probably more effective at net P retention. Yeah.
Yeah, are you seeing any kind of seasonal flux in phosphorus concentrations? Is it just pretty consistent with concentrations and then also with phosphorus, removals or sequestering in the wetlands, is that fluctuating seasonally as well?
I'm glad you asked that question because that makes me feel good about a meeting I had earlier. We decided to really drill down on seasonal aspects for our next paper on this topic because we have seen some interesting dynamics in the rivers as have others. Now we have just more water in the landscape during winter that used to be kind of frozen and bound up. And in the Lemon Fair, for example, one of the years we were monitoring saw this really neat trend where phosphorus concentrations just varied a lot by season. So if you have a flood pulse during one season with a higher P concentration, you're trapping more phosphorus than if you had a flood pulse in another season with a lower P concentration. We haven't unpacked all of that yet, but I think we're going to do that because it seems like with climate change, we just need to get used to how things are different now with all these winter floods that we're probably going to be seeing.
I have a few Zoom questions. So someone is wondering about soil types. So what types of soil retain phosphorus in wetlands?
Yeah, so the key metric, and this, depending on what type of characterization system you're looking for, what we're looking for often is soils that are high in certain forms of iron and aluminum that are more likely to hold on to phosphorus in the soil. And so those tend to be soils that are finer textured. So a lot of the soils we deal with are more on the clayey end of the spectrum, and they tend to have relatively high soil phosphorus storage capacity. If you are in a situation where you have a really sandy soil with low amounts of amorphous iron and aluminum, that would be the type of soil that isn't very good at holding on to phosphorus.
And then one more.
Yeah.
Could you explain ecological design?
I teach a whole class and I'm not sure we figure it out, but the idea of ecological design is really to integrate our understanding of ecosystems and ecology into the design process. So I would say this work is an example in that we are learning more and more about how these ecosystems function, and then we're using that knowledge and we're leveraging that knowledge to design systems that meet our goals. So by better understanding how the wetland P cycles in these ecosystems, we can then better inform restoration practices that will achieve water quality outcomes that are desirable. So when you have that interaction between ecology, ecosystems on one hand, and then the engineering and design on the other hand, a lot of magic can happen and good results. But ecological design is kind of like it's a big tent, as I like to say. This is like one little area of it, focusing on water quality and wetlands. It's a very popular area of eco-design work in the United States, but there's a lot of other topics that fall under that big tent as well.
Could you speak to how you initially identified the need here with the NRCS and just how they have been involved in creating the model and input and how that process has been?
I think the need. So every year when the Lake Champlain Basin program puts out a call for research proposals, they will list topics that local stakeholders have sort of elevated in the conversation to being potential topics of interest. And then one year, one of those topics was kind of phosphorus capture in floodplains and wetlands, because there was just a need to better understand how important that is, how do we account for it. And then Beverly and Rebecca Deal got a grant doing kind of the higher floodplains, and we got a grant doing the kind of lower wetland portions of the floodplains. And that just kicked off this whole process. And then we worked with NRCS to identify sites for that study. They became more and more interested in our work. And then through their SEEP program, they were looking to establish projects that test the benefits of conservation practices around the country in different regions. And so we were lucky that they were interested in launching a SEEP wetlands project in our region. And because of our prior work, we were kind of a go-to to lead that project. So it's just been snowballing ever since then, but it started with probably at a group, the steering committee for the Lake Champlain Basin program, somebody just really wanting to know more about how floodplains and wetlands affect phosphorus transport. So it was kind of stakeholder driven from the beginning.
You talked about how having well oxygenated water is one of the important factors for phosphorus retention. I was just wondering if you found like certain factors or traits that will show you that the water in one area might be more well oxygenated than in a different area.
Yeah, we've been trying to, Harrison's been working on ways to model this and identify where we're most likely to see low oxygen conditions. He's using machine learning, and so that's more kind of looking for patterns that we can observe and then predict where low oxygen conditions might occur. But from a mechanistic standpoint, which is becoming a bit more old school, soils with high organic matter that have a high oxygen demand, so where microbial life's really active and using a lot of oxygen, that tends to be why wetland soils can go anaerobic in the first place. But residence time is also an important factor. How long is the water staying in the wetland? If it's staying for a really long time, that gives more time for the oxygen to become depleted. And then there's factors like ice. Like we've seen some low oxygen conditions where we have ice cover, and we kind of go out there like ice fishermen and poke holes in the ice, and we measure low oxygen water underneath. And that's because there's just not diffusion from the air because it's capped off by that ice. So a variety of factors. Again, if we go to the worst case scenario, if we reflooded a cornfield and we let the water sit on there for a really long time and then let it drain off, that might be a situation where we're more likely to have gone anaerobic and generated that SOP release. So we've been thinking more like, is there sort of like a nice balance in terms of residence time? We want the water on the wetland long enough for the particles to settle. We also need to think about things like habitat, like waterfowl. But keeping residence time down a bit is kind of good for us because we don't have as much time to generate that dissolved P release that we worry about in some situations. So we're thinking about that more and hoping we can integrate that into the guidance we provide to NRCS.
Given the soil texture effect, do you think wetland restoration and buffer plantings work to reduce P are more or less effective on clay versus sandy soils, or even more important on sandy soils if they're not naturally good at retaining?
Can I say it depends?
Yes.
Yeah, I mean, it will depend on the situation. I mean, we just haven't encountered a lot of like riparian sandy soils in our work thus far. That would present different types of challenges, including that water can move through subsurface mechanisms more. We tend to kind of be able to just arm wave at that because we don't see a lot of infiltration. And if in the low spots on our systems, once it's flooded out, the water just stays. We're not having a lot of subsurface movement. So that's another thing in a sandy site you have to think about is you might be infiltrating through the soil and then kind of through base flow, that water is entering back into the stream network. But yeah, I'm not sure if I would say one's better or worse in terms of soils. It's just something to consider. A sandy site will work just as well for trapping particles, probably. And it might not have as much. One of the kind of weird things about this is those soils also will probably have lower phosphorus concentrations to begin with because they weren't able to hold on to the peat initially. So that phosphorus might have been long gone, and we're not worrying about it coming back out now as much as it hopefully makes sense.
All right, we have time for one more.
Considering how long this project's been going on and how many parts there's been in it, how have you seen your research and data applied to current conservation projects?
Yeah, so I think we have sort of our findings overall were good for wetlands being phosphorus sinks. So I think that has kind of given people more confidence to pursue wetland restoration as a water quality solution. I think ultimately as well, where we're going to land with NRCS is we're going to provide them with concrete guidance on like how to approach different restoration situations to get the best outcomes. And they are, like, if you're going to influence one stakeholder in this realm of wetland restoration, NRCS is the one to go for because they are engaged in this work all over the country. And so that's really cool to be kind of having a direct line to those folks. And then this kind of calculator tool, this we haven't achieved yet, but you know, I think we would be the first in the country to kind of give people a way to easily kind of estimate what the phosphorus retention in these types of systems would be. And my hope is that just kind of provides a lot of support for efforts on the ground, because instead of, you know, saying this is good, but not knowing really how to communicate how good, you have numbers, and the numbers people tend to want are like a mass of phosphorus retained each year. And so we're trying to get them to a point where they'll have that number and make those arguments.
Well, thank you, Eric, for coming in and giving this talk today.